Okay, so did everyone have a chance to read this? People who are interested? This is from an incredibly reliable website called marsdaily.com. Just talking about new software that was uploaded to the Mars rovers. This is from a few years ago. Field D-star, which is an algorithm we're totally not going to cover in this class, but it's like A-star, except that it can handle when the start state is moving. Rather than just running A-star all over again from the new start state, you try and reuse work from before. Plus, the problem, if the problem changes slightly, it can still try to reuse some of its work. So this is a path planning algorithm that was uploaded to the Mars rovers. Here's an animation of it. What happens is they have this Mars orbiter that orbits around the planet, taking pictures with a nice camera. And so they have nice pictures from way up high of the terrain of Mars. And from that, they can assess areas that are really not traversable by the rover. Like, they can see big rocks and cliffs and things, and they know, like, don't go there. So that's done in red here. It's like those, don't go there. This is like some rock that they want to see. And so they tell each day the rover what to do during the following day. They can't teleoperate the robot because it's like 8 minutes to Mars or something by radio wave or something. What? 8 to 16. So teleoperation is not good enough. So the rover takes a picture of where it is and says, here's where I am. And then the scientists go off and think about what to have it do, and then they upload a plan. But the plan is actually fairly abstract. So the plan will say, go visit that rock. And the actual detailed path planning is done by the rover. So the rover actually has a teeny bit of autonomy on board, except that the rover only has a very good sense of what's traversable from 3 meters out or something. Beyond that, there might be stuff hidden behind rocks or something. They might not have a good sense of exactly how bad the terrain is. So as the rover is moving, it acquires more accurate images. And so you can see the area where it has good information is in green here. And it does a first plan to get to the destination. And as it moves, it updates the costs in the world. Imagine a grid world where every cell had a traversal cost. So it's updating the traversal cost as it goes and replanning, updating the optimal plan. Running A-star from scratch is actually too expensive for this rover. When you send a microprocessor into space, I guess there isn't much atmosphere in space or on Mars, so high-powered electrons, which are called like gamma rays or something, anyway, are coming through, and if you have little teeny features on your microprocessor, they might get messed up by these gamma rays, apparently. I don't know anything about this. This is just what people tell me. So you have to buy a radiation-hardened microprocessor, which means that they're really slow and out of date. So you don't really have, plus they don't want it to spend all its processor power doing path planning. They want to actually analyze the data and send messages back to Earth and stuff like that. So they want a very fast planning algorithm, and that's why they use Field D-star. Anyway, it does incremental planning as the start state is moving and as your information about the world changes. So it's a very fancy search algorithm. It would make a good final project for an ambitious undergraduate or maybe a graduate student. But I just want to show you, it's used in very real life. There's a Mars rover running heuristic search. Okay, let's get on with today. So, no, I'm not sure I want to do any of that. We had a whole bunch of end-of-lecture questions. We had one. Well, I should rephrase that. We didn't have that many people turning in end-of-lecture questions, so I was disappointed in that because I like to think that you're all inquiring minds who are bursting with questions about AI. But one person tried to make up for it all by asking 8 questions on one piece of paper. So I'm not going to answer all of those questions. But I'll just go through the top 4 right now, and we'll do the other one later. Should we attempt to replicate human mental behavior? Or when we're designing an AI system, should we just, do the best thing, even if it's like superhuman? So this depends on what you're doing, right? If you're a psychologist and you want to know how people work, then trying to program a person into a computer is very helpful, because if you succeed in having a program that behaves like a person, then you have a sufficient but not necessary condition for human mental behavior. Like, it could be that people work like your program. If you write a program and it behaves nothing like people, then you know that people don't work like your program. If you write a program and it behaves like a person, you don't know that people behave like that, so it's not a necessary condition, but it's a sufficient explanation for human behavior. And that's kind of interesting, because right now we have like 0 sufficient explanations for human behavior. So having one of them would be great. So if you're interested in psychology and understanding people, then attempting to replicate human mental behavior is very important. So it all depends on what you want to do. So I guess this question is like, what should we want to do? And this is America, man. You do what you want to do. As long as it doesn't infringe on somebody else, go for it. I'm not going to tell you what you should want to do. Okay, so the second question is, how helpful is it to watch animal behavior? Like, are animals better at solving vacuum world than our programs? Well, I tell you, they cannot come up with better plans, because your program is going to come up with optimal plans every time with A* and a super awesome admissible heuristic you're going to make. So you can't find a better plan. Now, could you find it faster than A*? Well, I don't know. Your A* is going to be pretty darn fast. So I doubt any squirrel is going to beat your A*. Now, are squirrels better than A*? Like, I don't know. They're furry. A* isn't. I mean, if you like soft and cuddly, maybe you like squirrels. Although my guess is if you tried to cuddle a squirrel, it would like claw the hell out of you. So maybe you like your program better. I don't know. Squirrels have to do things like live outside in the winter and reproduce and eat nuts and stuff like that. So they're under a lot of constraints that your program is not. So, like, on that point of view, maybe I'm more impressed by the squirrel. But I don't know. This is like getting incredibly subjective. Certainly, I think people have said lots of cool things after studying animals. Like, somebody came up with a series of like 5 rules that if you make little artificial agents obey these 5 rules, they like behave just like an ant colony. And I think that's really cool. Like, wow, could there just be a 5-rule sufficient explanation for ant behavior? Like, people go on and on and on writing huge books about ants and how awesome they are. But if you can do that in 5 rules, like, wow. Like, computer science has just helped out, what's that called, entomology? I don't know. Anyway, the study of ants. Wow, that's great. Now, like, do I think we're, like, going to solve sustainable energy by studying ants? No, but I don't know. Are we going to do it by A*? I think A* will play a role, personally. If you look at the sustainable energy Christmas product of the year was the Nest thermostat, which has machine learning in it. The Nest thermostat. Yeah, you haven't seen this product? You don't own a home. You're not a homeowner. I have this home, so I'm very interested in thermostats. Thermostat. The Nest thermostat, nest.com. Yeah, it's this really awesome looking thermostat. It does machine learning. Like, it learns when you typically get up and stuff like that. Oh yeah, it's very cool. And it's got a motion sensor built in, so like it knows when you're there and it knows when you're not. Oh, the Nest learning, yeah, exactly. It sends you Christmas presents if you were good. I don't. So, anyway. Now, does the thermostat run A*? I don't know, but it certainly runs AI. So, AI is definitely playing a role here. Okay, the next question. This is a softball. I'll let you guys answer this. How feasible is it to solve vacuum world by just guessing which way to go, rather than doing like some fancy smanchy search thing with nodes and trees and yada, yada, yada. Like, what if we just like point in the direction of the dirt and go? Is that going to work?
Unless there's walls.
Yeah, whoa, there was. Damn it. Oh, it's not going to work. I mean, let me draw you a world where you will suffer if you are not thinking, which is like, I am here, and the goal is here, and there's a big wall right here. So if you just like, ouch, like, that's not going to work. And then you're going to say, okay, well, fine. You know, when I'm here, there are only two actions available, that way or that way. So I'll take one. I'll go that way. Okay, all right, smarty pants. Now, what's going to happen when you're there? Right? You're going to be like, oh, I'm going to take the move that's going to get me closer to the goal. You know which move that's going to be? That one, moving back down, because now you're not square root of 2 away, you're just 1 away, which is 40% closer. So you're going to be like, not getting anywhere. So don't tell me that just some like, just move in the direction of the goal is going to actually solve vacuum world. No. You need to think. You need to plan. You need to run A-star or some other nice search. So that's the answer to that question. That was a softball. This next question is like, are search algorithms actually any good? Why are you teaching them to us? And they're good because I say they're good, plus they're in the textbook. Plus, you're going to demonstrate they're good on your assignment. So don't tell me they're not good. And the last question I'll do next class because it just takes too long. Okay, whew, that was like one person's page. So this question I didn't quite understand. It was about high branching factor. So what do you do? What do you do with a problem with high branching factor? Sorry?
You just do it.
You just do it? What was the branch? You had some problem with a big branching factor, didn't you?
Yep.
Sequence alignment? Doesn't that have a big branching factor?
Well, it depends on how many sequences you're learning.
Yeah, if you're aligning like 10 sequences, then the branching factor is like 1,000? Yeah. So there was some other problem I was reading about where the branching factor was just like totally enormous. Like you didn't want to expand a node. It was so scary. We were just learning last class about some algorithm that you use when like the open list is getting too long. Beam search, yeah. So this person says, and I don't quite understand this question, can you learn anything from running a suboptimal search like beam search on a problem that has a large branching factor? Learn anything? So I didn't quite understand the question, but I think, I mean, would beam search work well on a problem with super high branching factor? I think so. Like you keep the K best kids. I don't know. There's a fancy algorithm that we totally don't talk about in this class called partial expansion A-star, where you just expand the kids that are good, and the ones that are not good, you don't expand, and yet this algorithm manages to maintain completeness. And you're like, how can that be? There's some children we didn't generate. But you summarize them in the parent and put the parent back on open. So if you ever decide that you're getting desperate for a solution, you can go back to the parent and expand it, complete its expansion. So totally not going to talk about that algorithm either. Is it always possible to devise a perfect heuristic for a problem? So I would turn that around and say, is it ever possible to devise a perfect heuristic for a problem? And like if it's an interesting problem, the answer is probably no. Otherwise, we'd have a perfect heuristic, and A-star would find the optimal solution without backtracking. And life, does everyone understand why? Why are we talking so much about search today? Does everyone understand why A-star is going to march directly to the goal with a perfect heuristic? Let's see why. Okay, so here's the root. It's like, okay, f equals 3. And then we generate some kids. And we have a perfect heuristic, right? Which means that we know that one of the kids is going to have an f value of... Somebody raise their hand, preferably someone with the right answer. 3. Yes, f equals 3. Right? G has gone up, h has gone down. So G is now 1. If right here G is 0 and h is presumably 3. here G is 1, and we have a perfect heuristic, so H is 2, so F equals 3. And then these presumably have a higher F, like, I don't know, 4 and 5 or something. So A star is going to expand this node. And it's a perfect heuristic, so that means one of the kids is going to have the same F value. This is going to be 3. And these other ones might be 3, but they might be higher. I don't care. If it's a perfect heuristic, then, and if these don't lead to goals, then it has to be higher. In fact, if H is 2 from here, then it's going to be 3 from here if you can undo any move in the search space. So G is going to be 2, H is going to be 3, so F is going to be equal to 5 for these other ones. Anyway, so you're always, if the heuristic is perfect, you're guaranteed to have one child that's got the right F cost. So A star will just march down the tree to the goal. So usually we don't have a perfect heuristic, so it's amazing when we do. Just totally amazing. That's why I showed you some paper where someone claimed they can compute a perfect heuristic in polynomial time, and that's just for some like very narrow subclass of problems. And so we're even excited if someone can do it for some subclass. It's like they get a paper and we all go to the conference and hear about it. Are we going to write a CSP solver? No, I'm sorry. We only have 5 assignments. I would love to add assignments, but we'll see how you feel at the end of the class. I'll ask you if you wish there were more assignments or fewer, and we'll see. It's a great idea for a project. There is going to be a teeny gap. I think this assignment is due on Monday, and I'm not going to hand out the next assignment until Wednesday. So you do have this little 2-day gap. Feel free to write a CSP solver. It's not hard. It's only depth first search. You've already done depth first search. So, give it a try. But great class project idea. Write a CSP solver. Okay, this is a question someone else in the class is going to answer, not me. With constraint problems, it seems like you might end up checking a lot of duplicates. For example, we might color Queensland and South Australia and New South Wales, or we might color New South Wales and then Southern Australia and then Queensland. And that would leave us with the same set of variables that didn't have values. Everyone remember the map of Australia we did last time. So someone help me here. Are there duplicates in this search space? Lee?
I don't think there are.
Why not?
Because of the
Domain elimination. We did this fancy forward checking thing. Is that what you're talking about? Let's leave forward checking out of this. I love forward checking. Forward checking is near and dear to my heart, but we can deal with this question even in a state of ignorance where we pretend we didn't even learn about forward checking. If we just look at this search tree, when I branch on which color to color South Australia, so here I color South Australia red, here I color it green, here I color it blue, are there any solutions in common among these subtrees? No. Each branch creates disjoint subtrees. Like down in this entire subtree, South Australia is green. Exactly. End of story. Nathan.
There's no duplicates because you always check the variables in the same order.
No. Don't tell me this. That's the next question, is about heuristics. But no, you don't have to check. I mean, here, when I go down this branch, we did Western Australia. Yeah. But I could just go, when you go down the green branch, I can color Victoria if I want to. Okay. Don't tell me I can't color Victoria. Okay. Whatever I want. And coloring Victoria rather than West Australia doesn't mean that Southern Australia is no longer green. Does it? No, it does not. These subtrees are completely disjoint. Okay? Does everyone understand why there are no duplicates and we can do depth first search without any kinds of transposition table or closed list or even cycle checking or whatever, and it will work just beautifully? Okay. Dan.
Branching on the decisions, not on the neighbors. Yeah, you're branching on red, green, blue.
Those at every node you select a variable, and each branch corresponds to selecting a different value for the variable. Yeah.
That's why there can't be duplicates, because it considers all cases where
we don't have red, green, blue, red, or something like that. We branch on each choice exactly once.
the choice is implicitly
Mutually exclusive and collectively exhaustive. Yes. You had the idea. I like it. Okay. Yeah, so everyone understand. Now, there is a complication, which is like, maybe it doesn't matter which color we color South Australia. Maybe they're actually identical subtrees if we just relabel the colors. That's called a symmetry. It's not really a duplicate because it's not exactly the same solution. But if we just did everything except for every time we wrote G, we'd think it was R, and every time we wrote R, we'd think it was G, we'd get the same shaped subtree here as we did over here. So there are lots of symmetries in constraint satisfaction problems usually. I mean, even here, I didn't go bother writing Tasmania, but you can tell Tasmania is always going to have two legal colors. Just whichever one Victoria was, you can't color Tasmania, but either one, the other two doesn't matter. So there's always this little symmetry, no matter what we do. So that is a big problem in constraint satisfaction. There's an enormous amount of work in automatically detecting symmetries and removing them and fancy schmancy stuff that we're totally not going to talk about in this class. I just want you to know what constraint satisfaction is and how to implement a simple solver for it. I want you to understand forward checking. We're going to talk today about arc consistency, and then you know the basics of constraint satisfaction, and you can hold your head up high as someone who took an AI class. But yeah, symmetries, that would be a class project-y kind of thing. Maybe even too hard for a class project. Did you have a question, Frank?
You answered it.
Okay. Phew. Okay. All right, so that's that end of lecture question. Two more. Didn't get this one. Well, I don't know. Maybe I'm trying to read too much into it. Could you solve vacuum world backwards? Find a path to drop dirt in these specified locations. Yeah, you think you could do that?
Yeah.
How would you do it?
Go places that aren't dirty and then drop dirt on them.
If you could solve it backwards if you knew the start state.
Yeah, you would just go and find
If you knew where dirt was supposed to be.
Yeah.
You could solve it backwards.
Yeah.
Yep.
You would just go.
And you could do the same sort of framework.
Path,
Yeah, you'd have it be a shortest path kind of a search. You do something like A star. You wouldn't do depth first search. It's not a CSP. It's a shortest path problem because if you're trying to find the cheapest way to place the dirts.
I feel like it would almost be the exact same thing.
Yeah.
Wait, in this case, we're just making a dirtying robot instead of a vacuuming?
Yeah.
You have a lot of
You-
start states.
You can think of it as doing dropping refugee supplies at various camps, I guess.
If you're going forward and cleaning up dirt, you know you have one start state. But if you're going to drop dirt off, you can start at any of the dirt locations.
I'm going to start where I am. Thank you very much. Now, I have a choice as to which dirt place I could visit first, but we have that same thing when vacuuming.
I guess I was imagining completely backwards plan so that you start at a dirt location, drop the dirt there, and basically like playing a tape backwards.
So we know where we want to end, but we don't know where we start.
Right.
Yeah. How do we deal with that? Anyone have a thought about that? You've been talking a lot. Somebody else. Kendall, any thoughts? We don't know where we want, which dirt pile we're going to end at. Woo! Yeah. If you want to think about it in the state space, you can think of making a dummy start state, which is I'm at the virtual goal, and then there's some magical actions that teleport you to all the different dirts that you could have ended at. And then you go and do your normal search the way you normally do. So they have a virtual goal that you end at. I had a problem exactly like that once. I was planning for a big printing system, and it has a bunch of output trays. And for reasons I don't want to go into, we had to plan the sheet of paper backwards. We did it in order to make sure that sheet 2 came out after sheet 1. So we knew it was coming out after sheet 1. And then the question was, well, which output tray is it going to end up in? We might not know that, especially for the first sheet in the job. So we had a virtual destination, which then magically teleported to each of the trays, and then we planned backwards to the feeding tray. So this actually happens in practice. Amazing. Okay, so I think we dealt with that one. Okay. Is it possible to remove the problem of domain wipeout in a forward-checking search? What's domain wipeout? Anyone remember what domain wipeout is?
You don't have like a valid move.
Yeah. We had this here. Did we come up with a wipeout? We didn't. We were doing forward checking and everything was just dandy. Oh, here we thought about well, yeah, if we only had 2 colors for coloring, like say the Northern Territories really decided they did not want to be, I don't know, blue or something. We can't color them red because of South Australia, and we can't color them green because of Western Australia, and blue's not an option, so then we'd have a domain wipeout. I mean, I don't view that as a problem. I view that as a wonderful thing. I mean, we've just decided that we don't have to look in this huge subtree. So I guess I'm just an inherently optimistic person and glass is half full kind of guy, but I think domain wipeouts are great because we just saved ourselves a whole subtree of work. Now, you could say, so maybe that question is asking, can we arrange things so that we would never get into a domain wipeout kind of situation ever? And let's think about that. Could we ever have an algorithm that would never encounter domain wipeout? What would that mean? That would mean that we would assign a variable, and then we'd do some kind of super fancy forward checking on steroids, and then we'd set another variable and do super fancy forward checking on steroids, and we'd never hit domain wipeout, so there'd always be a feasible value, so we'd just set variable after variable after variable, and then we'd be done. And we could solve any CSP in linear time with just n decisions.
What if the CSP can't be solved?
Oh, yeah. Ouch.
Don't you need domain wipeout for that?
Yeah. Exactly. Now, so one of the beautiful things about CSP solving that you'll see if you choose to do a final project in this is that there's this kind of yin-yang duality between, do I spend a lot of time thinking about the constraints and doing what's called propagation? Forward checking is a kind of propagation where we propagate the decision that we made about South Australia out to the other variables. Do we spend a lot of time doing that, or do we just do more search? Like, do I think or try possibilities? If I think too much, then maybe my search is going to be really slow. If I don't think at all, I'm going to visit these huge subtrees. So there's this tension between constraint propagation, which is sort of a form of inference, and search, just trying the possibilities. So that's a cool thing about CSP solving.